is a freedel integral of unknown density of state of the sample with some function which is known. If you know the density of state of the tip, if you know the temperature at which you measure, this function is totally known. So in terms of matrix, this is something you measure, this is something you would like to know, and this is what you know. So you know 2 of 3, so by inversing the matrix you can get really this density of state of your sample. Okay? It is only theoretically working, believe me. No one, for instance, because of the noise. Because of the noise, experimental noise. But in principle, it's nice.
Dimitri, how well known is usually the density of states of the tip?
Good question. Okay, good question. So the stupid answer would be that we take metallic tip, and in the energy window of interest, the density of state is constant. Okay? A more detailed question could be, for instance, if I want to use a superconducting tip, I will put and just normal metal tip in a superconductor, and then I will retract. I will get a cluster of superconducting material, and I can do a spectroscopy. I know the density of state of my lead, for instance, which was measured by Ivar Javer. I will come in a few minutes with very high accuracy. And so if I get my result is a convolution of 2 BCS density of states, then I know the density of state of my tip.
But you also have a kind of spatial confinement at the end of the tip. Does this play any role?
Yes. If it does, I will have a deviation. So I invert the problem, and I say I have a known sample. Then I get a tip, and with a known tip, I go to unknown sample. Okay, so if the density of state of the tip is considered as a constant, we can get it out of the integral and get this very simple formula in which the derivative of the current with respect to the voltage is just proportional to the density of state of the sample times the derivative of the Fermi-Dirac function with respect to energy. And this derivative is just a bell-like function. In fact, yes, this one is okay, not opposite. And the width of this height width of this is of the order of 3 times kBt. Okay, so if you go to very low temperature, then this becomes just a Dirac delta function, and you end up with very simple expression. Okay, so the derivative, or tunneling people, we call it tunneling conductance, as a function of applied bias, is simply proportional to the density of state in a position that we measure at an energy, Fermi energy minus bias. Okay, so Fermi energy here comes for 0. Okay, so from this we have typically 2 modes. One is constant height mode, in which you approach the tip, you get some current, and now you start to move the tip laterally, and you measure the current. For instance, if you have, for instance, atomic step, of course the tip sample distance will increase, and the current will reduce. Okay, this is one way, and another way is more intelligent and more often used, more safe, let's say, because in this case it was nice because I had a step backwards, but if I would go in opposite direction, I had a problem. So instead of doing this, what we can do, we can get instantaneous value of the current, check if it suits to us, and apply a voltage to the piezo in order to retract or to advance the tip, that the current remains the same. Okay, so if the current is too small with respect to we decided, it will approach the tip. If it is too large with respect to what decided, we retract the tip. In such a case, the tip will approximately follow the shape of the electronic wave functions. Okay, and finally we get sort of contour of the wave function of empty or occupied state depending on voltage we apply. Okay, that is why here in this region, when we have plus 2 electron volts. So it means the sample was biased by energy with minus 2 electron volts. You go to the empty states of the silicon, which is here, and if you go if you polarize your junction with minus 2 electron volts, you probe the occupied state near the gamma point. Of course, the STM, and this is a very bad thing with the STM, is absolutely insensitive at the first approximation with K space. Okay, so we're averaging over K space, and the weird thing that the way we average, we don't know. So the matrix elements, they are spectral, and so there is some problem with this. Okay, but we will discuss it a little bit later. So the message, main message of this first half an hour, that STM doesn't see atoms, but amplitudes of electronic wave function at different biases, energies. Okay, now I will give you very few examples of use of STM, specifically underlying the question of spectroscopy. So in 1993, so look, here we are just 10 years after discovery of STM, Cromie and Egler in ABM lab, they already have 4 Kelvin STM working in ultra high vacuum coupled to growth machine. You imagine. The first STM, it is presented in Basel University, in just a unit and table working in air, and 10 years later they come up with this. So what you see here is atomic steps on copper 111 material, and so these are flat, atomically flat steps, and if you look here, there are very strange things. There are some waves and some round stuffs around voids. If you look closer, here there are some copper atoms missing, and around these copper atoms, the STM observes some waves. These are freedel oscillations. These are standing waves due to the interference of surface waves or Shockley waves with some defects. And in this case, the defects are of 2 kinds. First, a single step, atomic step, and voids. Okay? And the wavelength of this interference pattern is the same for all image, but it depends on bias. For instance, here at plus 0.3 volts, you see it is like this. If you reduce and you go lower and lower, the amplitude increases, but specifically the wavelength of these oscillations increases as well. So if you plot the energy as a function of K, which is 2 pi over lambda you measured, you get parabolic dispersion, and it is nothing more than the famous parabolic dispersion law between energy and K value. So you can measure it just by measuring with STM. Of course, yeah?
Where are the copper atoms?
I think these are voids. Copper atoms are here, everywhere. So it is. So what you see, this is just single atomic step. It appears very high, okay, because it is very much extended artificially, okay. And this is atomically flat surface, so you don't see you don't see individual copper atoms, and you don't see them because if copper is good metal, in good metal you have planar waves, and the block amplitude of planar waves equal to 1, and you have no reason to see any atomic resolution.
Could you go back one slide? Because you say it's one atomic layer high, but in the upper right corner there are steps.
Yeah, but it is not.
Artifact?
Yes, it's an artifact.
Okay, because
yes, this is an artifact. All the atomic steps, they have exactly the same height. Okay, so we can easily understand this if we all images, if we consider that for each direction we have a planar wave coming in and a scattered wave, and by taking in account all possible angles, we can find that the derivative of the current with respect to voltage, this conductance which is measured, just 1 plus Bessel function with a 2k x spatial extent. Okay, and it works very nicely. And that gives you immediately an idea, not immediately because now we are in 98, idea of, okay, so I have a copper, imagine I have a copper, completely perfect copper plane, okay? In such a case, it is very difficult to get atomic resolution because my electronic waves are just planar waves. So the amplitude of atomic resolution, the modulation is extremely tiny. Typically, it is 0.01 angstrom. It is possible to observe, and we do, but it's difficult, okay? However, if you have scatterers, then you have these scattered waves, okay? And now, if I look on this scattered image and I do a fast Fourier transform of it, I get characteristic scattering vectors that resulted in this image, okay? And all these, they sit in equi-energetic level that provided this image. If I do it for Fermi energy, I will do all K-space imaging of my scatterings, which are related to the Fermi surface. Okay? So I can map somehow the Fermi surface, and this is just 2 times K Fermi. So you see, this is a Fourier transform of this image that looks weird, but it gives in Fourier transform a very nice rounded shape because the Shockley waves in two-dimensional, in 111 silver, I think it was silver, they form just a Fermi cylinder, okay, with a constant Fermi energy. Okay, you can play also with STM by producing staying waves. For instance, here there is a 1 step back, 1 step down, and then 1 step up. So it looks like a groove. Or you do a succession of atomic steps, and if these atomic steps are not far each from others, you can also interfere electronic waves laterally, and depending on bias, observe some eigenvalues. So for instance, here you have just 1 maximum, here you have 2 of them, so you couple your planar waves to resonant modes of your cavity. Okay? And this is energy dependent. Okay? Now, of course, you can go furthermore, and you can try to see, for instance, if you have 2 voids close in each other, you can see that they can interact. It is not just a superposition of simple interferences. Moreover, for instance, here at 30 Kelvin, my former PhD student put cobalt atoms on silver 111, and what you see that the atoms move. Of course, this is accelerated image, but what you see that there is a typical distance between atoms. Typically, they form dimers. Okay, of course, the thermal diffusion breaks these dimers, but there is typical distance. In fact, the second atoms likes to be in the minimum of the interference pattern of the first one. So they interact via Shockley waves. If you cool down the system, of course, you can get these very nice images by manipulation, obtained by manipulation of individual atoms in Don Egler group in ABM. And then you couple your planar waves to proper modes of these resonators, and you can strongly amplify them. Okay? But the physics behind is very similar to this experiment that I did on my own with a loudspeaker and water. Okay? But the message is the Fermi liquid is a good liquid because the behavior you get is exactly like a liquid, like a classical liquid. Okay, last example before I go to superconductivity.
Question.
Yeah.
What about the phase shift. Can you measure a phase shift? For example, if you have a magnetic impurity.
Yes, you need a phase shift. You need a phase shift. I will come to this just in the second part of the lesson. Okay, for Shiba states we do. But even in this image, if you want to fit it with a bezel, you need to introduce a phase shift on the scatterer. A very nice example that was produced by the same group already 18 years ago was to put cobalt atoms, which produce a very nice phonoresonance on copper. So you get this Kondo effect due to screening of electrons of copper due to of the magnetic impurity, and it manifests itself in this DI/DV tunneling conductance I discussed it before as a minimum near zero bias. So if you look on the topographic image, of course you have atom, but if you look on this minimum, you get this spot, which is a signature of Kondo effect, local signature of Kondo effect. You don't see this signature here or there away from cobalt atom. Okay? Now the experiment which was provided was the following. They created an elliptical resonator, not circular but elliptical, and the nice thing with elliptical resonator that it has two focal points conjugated. And they put one cobalt atom in one of the points, nothing here, but then when they did spectroscopy, they observed the minimum in the void. So it means that the information about the Kondo effect here was sent few tenths of nanometers away on the atomic scale. Of course, if they put this atom away from the focal point, nothing happens. Okay? Now we are done, and we are in 1973, and this story of Ivar Djaver, who doesn't believe to tunneling, and who gets a Nobel Prize by measuring the density of states of lead, and he observed the superconducting gap in agreement with the BCS prediction that in a superconductor, in a superconducting state, you have a superconducting gap of width of delta, which is in a weak coupling limit is related to critical temperature. And this superconducting gap is temperature dependent, and it closes at Tc. Moreover, the second part is that you have particle-hole symmetry, so you expect around the Fermi level the gap to be opened on both sides. And then the feature of superconductors, which is known at the moment that STM is discovered, that there is a vortex lattice, and this is the result of Bitter decoration. Many of you know this experiment already in '67. So the question is, planar junctions exist well before STM. Vortex lattice is discovered before STM. So what STM can do? It can study quantum vortices in a different manner. In Ginzburg-Landau theory, the vortices are singularities of the wave function, and they are 2π singularities of the wave function. So the gradient of the wave function diverges as 1 over r, where r is a distance to the vortex core. As a result, the order parameter goes to 0. So there is one singular point in which superconductivity is fully suppressed. And around the vortex there are currents that of course they are 0 in the middle. They rise with the same as the order parameter on the scale of Xi, and then they decay on the scale of lambda. And Abrikosov found a solution near critical magnetic field, which is periodic solution, that these vortices, which are energetically impossible in ground state, at zero magnetic field, they become minimum energy solution in the magnetic field. And so these vortices are vortices of currents. There are also cores where the order parameter goes to 0, okay? And of course, each vortex contains a single flux quantum, as you know. So how STM can measure them? It can measure them because, as Djaver proved, there is a gap in the quasi-particle spectrum of a superconductor, and if in the vortex core the gap, the superconducting state is suppressed, then necessarily something should happen with the tunneling conductance. It should be that of normal metal. So, for instance, the first experiments were done on a strange superconductor which is called niobium diselenide, which is, which is a lamellar material. A nice thing of this, you can cleave it at room temperature in air, and the surface is protected by selenium layer. You can rapidly put it into the STM and cool down, even if your STM is not UHV. Okay, that's why first experiments were done on this material. It has a superconducting gap, and these are results, just recent results from our group, but there are a lot of groups. The first was Hess in Bell Labs, then Sudarev and Vieira in Universidad Autónoma de Madrid also worked a lot. Christoph Renner, our group as well. So there are a lot of groups in the world who use this material. The gap does exist, so STM works, shows the gap as planar junctions. Also, we see that here the gap is not as BCS would predict it. There are some strange things. It's not sharp edge, but some smoother one. And using this contrast between the gap, no gap, gap, no gap, Hess was the first to show that the vortex lattice is resolved with STM as the black holes is the positions at which the superconducting gap in the tunneling density disappeared. So it is completely artificial image. Nothing happened in reality on the surface. You just measure locally density of states. If there is a superconducting gap, you put white point on this image. If there is no superconducting gap, you put a black point. You do your spectroscopy, you move step further, you do the same, you do step further, and 24 hours after this, you finish your image and you get all this stuff. Okay? So this was the proof that the STM measures the vortex cores. Now, there is something strange there, that depending on bias inside the superconducting gap, the superconducting gap is 1.3 millielectron volt here, approximately. But if you look on the tunneling conductance at zero bias, it has a six-fold star shape. And moreover, if you follow the tunneling conductance at zero bias, you see that in the vortex core, the tunneling conductance doesn't become normal, but shows a peak. And this peak corresponds to the bound state called Károlyi-Matrikon-de state, because the normal core is a place where normal electrons or quasi-particles can exist with no problem, while they cannot exist in the superconductor because of the gap. So it's like a quantum well, the vortex core, like a quantum well. You know quantum well? You have electrons here and barrier outside, so you have some bound states inside. Okay? The only difference between semiconducting quantum wells and this is that you have very specific boundary conditions, because the phase turns 2 pi over the vortex core. This makes a very serious difference. And they were sorry, Herman, I turned it by 90 degrees because I had no place. A lot of works were done to understand where this six-fold shape comes from. And the group from Madrid did a lot of work on it, using in particular tilting fields in which they can probe different, so the orientation of tunneling current is the same, but the orientation of the field is not the same, and so the vortices get out at different angles, and this was a very precise measurement. I invite you to read this recent paper, but inside of this recent paper there is a very huge literature of what was done before. So for a review on vortex physics in conventional superconductors, I can suggest you this Herman Sudarov and Sebastian Vieira review. And of course, STM is not the only techniques to see vortices. Magnetic force microscope was the first to reveal vortices in YBCO, while STM failed STM had real troubles to reveal vortices in high TC superconductors by a reason that I will explain just in 2 minutes. And of course, then scanning Hall probe, this was done in Bath by a group of our MC member, Simon, already in 1997. And here, for instance, in YBCO, you clearly see that twin boundaries, YBCO is almost squared lattice, and you see that twin boundaries play an important role in pinning vortices, which are organized at 90 degrees on this lattice.
The previous one is here, so it's not clear, it's because of.
Okay, it's separated subject. I wanted to tell just that STM is not a tool that you can apply to all superconductors. In some cases, it's very complicated. For instance, there is a new family of superconductor pnictides, and STM fails in most of them. There is only one, which is iron selenide, which is more or less works as we want. We see vortices, a good gap, but in many other materials of this family, the gap, the excitation spectrum appears very strange, and we are not able for the moment to understand where it comes from.
Another energy?
Sorry?
Small angle neutron scattering was very well employed on many families of superconductors.
Right.
Looked at square to hexagonal transitions.
Right.
And it works for superconductors that don't cleave well for
Exactly. Exactly. But this indeed, neutron scattering worked very nice. Basically, the first indication about the Abrikosov vortex lattice was done by neutron scattering, not by the bitter decoration. So, but this is a technique which is space integrated. Okay? So if you have a vortex lattice which is so disordered, it's very difficult because you will have just a halo. Because it's finally, neutron scattering have a diffraction pattern of neutrons. So you need some ordered lattice to do it. Okay, so a key experiment that supplied a proof of D-wave character of superconductivity in HCC was provided by Kirtley in this famous 3-crystal experiment in which Hélène Raffi from Orsay provided a sample made of YBCO film with 3 distinct orientations. And these 3 orientations were made in the way that if the material has a D-wave superconductivity, changing the phase 2 times over 2 pi, then in the center, a vortex could be only pi vortex, not 2 pi vortex. Okay, and you can see that in here there are trapped vortices. Don't look on that because they are partially Abrikosov-Josephson vortices. But all vortices which sit in each material provide in this squid measurement exactly the same amplitude, except this one that sits in the center, and it was a proof that it is not 2 pi vortex but pi vortex, so there is a half of flux quanta penetrating in. Okay, now to finish this first part, I will just tell you about superconducting gaps. So you already saw that STM, similarly to planar junction, is able to measure superconducting gap, and the nice example is this one. It was a work by Pan Davis. Pan was a PhD student of Shims Davis at that time in Berkeley University. And in 1998, they measured this nice result of niobium on gold junction. So it's at that time the tip was superconducting and a sample was gold. Okay, and what you see here, it is a set of experiments at different temperatures. Okay, and the points are experimental data, and the solid line are just fits by BCS with no free parameters. Okay, so you see that STM is just a solid tool of good gap. The only problem is that this is the only example when it works so nice. Okay. Now, if you go to MGB2, a material which was discovered in 2001, superconducting, material itself was known for decades, that was a mess. Immediately in archive, we had hundreds and hundreds of tunneling papers suggesting very different scenarios and giving very strange results. And we started to measure that time. They were pellets, some powders of MgB2. So basically the samples were produced in the following way. We took a silicon wafer, we put a silver print, we put a powder alpha SR on it, so it dried, then we removed all the powder which was not glued and used it as a sample and measured. Okay? In approximately, so we measured several thousands of spectra, and most of the spectra, meaningful spectra, contained a small gap, like this one. I don't show it. But there were few